Hi everyone. Today's topic is solving trigonometric equations. And what you've learned in your algebra, we're going to use standard algebraic techniques to isolate the trig function. And we're going to do that, and you'll see those as we go along through our examples. After that, we're going to find the solutions. Now, a unit circle would be handy on this, and when we go for the x that is with which is actually the angle that we're looking for. So on this first example, solve sine of x minus 2 equals negative sine of x. Now we're trying to isolate the trig function, so I'm going to add sine of x to both sides of this so that it's not in two places. And right here I get 2 sine of x plus sine of x is 2 sine of x. Minus 2 equals 0. So I'm going to add 2 to both sides here. And I got 2 sine of x is equal to 2. And I'm going to divide both sides by 2. And I've got the sine of x is equal to 1. Well, where's sine of x equal to 1? Right there. It's the y-coordinate, if you'll recall. Sine of x is equal to 1. So, what is that angle? That angle in the unit circle, that is pi over 2. X is equal to, the sine of pi over 2 equals 1. And that's the only place that would happen in one lap around the unit circle. But if I were to go another rotation, find a coterminal angle with that, the period, if I add 2 pi to that, the period is 2 pi for sine, if you recall. And I'm just going to put an n here. And anytime we use an n here, n is an integer. So 2 pi times n, that gives me all the coterminal angles with pi over 2 as well. So there are infinitely many solutions. And I'll kind of show you why. If you recall, if I draw sine of x, kind of goes like this. Well, where does it equal 1? We would just keep going, on this and so on. And if I go this direction, up here it equals 1 as well. There are infinitely many solutions because it's the number of times it hits the 1 right here, and this describes it. With sine and cosine, it would be safe to use the 2 pi because that's the length of the period. Now, tangent, that period is pi, so we wouldn't be using 2 pi, we'd be using pi when we were to describe all the solutions. We'll see if that comes into play in some of these other examples. On this one, I'm going to add 3 to both sides. I've got 4 sine squared x equals 3. I'm dividing by 4. Remember, I'm trying to isolate the trig function. And I've got sine squared x is equal to 3/4. And I'm going to take the square root of both sides, but when I take the square root, I got a positive square root and a negative square root. So that gives me sine of x. And then I've got plus or minus, and then it's the square root of 3 over the square root of 4, which is radical 3 over 2. Sine of x equals plus or minus the square root of 3 over 2. So if you're looking at your unit circle, that's up here. This is pi over 3, right? And the x-coordinate's 1/2, and the y-coordinate's square root of 3 over 2, and that's what we're looking for. So if I write down, I've got x equals pi over 3, and I think right here you would get the same thing. So this is 2 pi over 3. I'm going to write it like this, 2 pi over 3. And then I would come down here, just trying to think. Now, the coordinates here, negative 1/2 and negative radical 3 over 2. This one was negative 1/2 positive radical 3 over 2. But remember, we have positive radical 3 over 2, which give us these two. And then the negative ones down here. So if you're looking at your unit circle, let's see. This is 4 pi over 3. Okay. And then if I come down here at positive 1/2 and negative radical 3 over 2. Let's see. This is 5 pi over 3. So I could write pi over 3 plus 2 pi n, 2 pi over 3 plus 2 pi n, 4 pi over 3 plus 2 pi n, oops, and 5 pi over 3 plus 2 pi n. Now I'm going to, gotta quit doing that. I'm going to try to be a little more efficient, even though I've already written them out. If I add 1 pi, pi over 3 plus 1 pi, that's 3 pi over 3, that's 4 pi over 3. And then if I add pi to that, I'll be at 7 pi over 3. So I'm going to consolidate these two because they're right here. They're on the same diameter. I'm going to write that as pi over 3 plus pi n. That takes care of everything that these two describe. And this one I'm going to write 2 pi over 3 because they are on the same diameter. And you just go pi units, and then another pi units, another pi unit, another pi, 2 pi over 3, a little sloppy there, plus pi over n. This is a little more efficient. I keep wanting to write that fraction, and I finally just went ahead and did it before I caught it. Okay. Okay, you are seeing why I don't use these pencils very often. Okay. A couple more examples. Example 3 here. Solve sine squared x equals 2 sine x. So here's what I'm going to do. I'm going to get everything on one side. And I've got sine squared x minus 2 sine x equals 0. And then these both have a common factor of sine x, so I'm going to factor that out. Sine x times sine x minus 2 equals 0. And now I've got the zero product property, so I'm going to set each factor equal to 0. Sine x equals 0, or sine of x minus 2 equals 0. Now, when sine of x equals 0, where is that happening? That is happening, sine is 0 here and here. So it x will equal 0, or x is equal to pi. And if I add 2 pi in here, and if I add 2 pi in here, that would work. It's not, let's clean it up a little bit though. See, this is 0, 2 pi, 4 pi. This is 1 pi, and then you add 2, that's 3 pi, and then 5 pi, 7 pi. So it looks to me like we can just say in one, oh mercy, in one step here that x is pi times n. Okay, let me solve this side now. If I add 2 to both sides, I've got sine of x equals 2. And does the sine ever equal 2? It seems to me like 1 That's the y-coordinate. This is the highest point you're going to get. 1 is the high point. Sine of x, so this part is, there's no solution on this part. Sine of x does not equal 2. That's undefined. So this is our set of solutions there. And then one more, example 4. Okay, now I have actually forgotten the secant and tangent, secant squared, tangent squared. I'm actually going to write this in tangent squared form. And here's what I do. If I've forgotten, I do remember sine squared x plus cosine squared x is equal to 1. Now, I want tangent. So I'm going to divide by cosine. I'm going to divide this by cosine squared x, this by cosine squared x. This is what happens. When I forget, I'm going to derive it from the one I do know. I do know this. So, okay, I'll take that call a little later. I got 3 secant squared x. All right, so remember what I was doing. So I got tangent squared x plus 1 equals 1 over cosine. That is secant squared x. All right. And then if I subtract 1, no, I don't want to do that. I want this. I'm going to replace secant squared x with tangent squared x plus 1 minus 2 tangent squared x minus 4 equals 0. So this is 3 tangent squared x, I just broke it again, plus 3 minus 2 tangent squared x minus 4 equals 0. 3 minus 2, that is 1 tangent squared x. 3 minus 4, that's minus 1, and that's equal to 0. So if I add 1 to both sides, I got tangent squared x is equal to 1. Well, where does that happen? Well, I'm going to check my unit circle again. Going to that every time. I think that happens at the pi over 4s here. Remember, this is square root of 2 over 2 and for the cosine, and square root of 2 over 2, and cosine over cosine is 1. So the tangent's 1. So x is pi over 4. And over here, negative radical 2 over 2 and negative radical 2 over 2, that would be 1 again. And this is 1 pi, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. But I think this is, again, on that same diameter that we can just go pi, 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 just keep adding pi. So I'm going to write all the solutions as x equals pi over 4 plus pi times n. And n can be positive or negative. We could go in this direction and have the negative values for the x there also. All right. You guys take care.